Sir, you are muted.
Okay, let's see. I hope you can hear me now. So last time I was saying that the last time we did exponential distribution, and I'm just trying to recall that. So x, let x be a continuous. So we are talking about continuous right now. So all are continuous here. And so let x be a continuous random variable, and then x is said to be a exponential with parameter lambda, and it is denoted as this. So all the distribution has certain notations that we should be careful of. So it is defined as exponential if the PDF is given as follows, where fxx is lambda e to the minus x when x greater than 0 and it is 0 otherwise. So these are the PDFs that you have to remember. It's a good thing to remember, because in a lot of applications of probability, if you remember this, then you can immediately see where the problem belongs to. So you have to really remember this PDF. So if I plot this graph, then for various values of lambda, so this is like lambda equals to 1 here, and this is like lambda equals to half. Okay, so we can plot these values, these curves for various values of lambda. One thing we note is that this is like decaying. Okay, so this is the decaying function, and then obviously another thing that we check is like, and this is defined over all x greater than 0. So this is like 0 to infinity. Fx dx must be 1. Okay, so these are the conditions that it must satisfy. The CDF will be given by this, right? So this is how we define the CDF. CDF in general is fxx is minus infinity to x, right? And then this is like the PDF of so let us say this is fxu du. Okay, so this is how the CDF is defined, but then minus infinity to 0, it's 0 anyway. So that's why we started from 0 to x now. Okay, so this boils down to 0 to x, and then we integrate it, and then this is the result of integration. So this will be outcome will be in t, obviously. Okay, so okay, why outcome will be t? Outcome should be in x, right? So there is a typo here. So outcome should be in the variable x. Okay, so you can verify these things. Okay, the integration and all this, I will leave it up to you. These are simple integrations. Unless there is a tricky integration, I will do that. Okay, so expectation of x will be given by always it's like minus infinity to infinity, but then these things boil down to 0 to infinity, because the valid range of x is indeed 0 to infinity. So that's why the limit goes from 0 to infinity. And we know that in expectation we have x times the PDF of x. So that's what we did, and then we integrated. So I leave this up to you to find out. So these are simple integrations. So this is what we will get. The expectation of a random of an exponential distribution is 1 over lambda. Okay. And then we would also like to know the variance of the exponential. So for variance, we know that variance is given by expectation of x squared minus expectation of x whole squared. So this is what we need, because expectation of x we found this was 1 over lambda in the previous slide. So that is we already have. So expectation of x squared will be x squared times the PDF of the exponential. So I did a substitution. I believe I did a substitution here. Lambda x is y. Okay. So x square will be y square by lambda square. So y square by lambda square came here, and lambda x is y. So this is the y here, and and then we have converted this also in dy form. Okay, so so here yeah, so this will be like the things that I leave it up to you to verify. Okay, so this is like verify on your own. Okay, how this integration is results in this. Okay, so you do integration by parts. So this is like integration by parts. You have to remember these things, integration by parts. So these are the things you do in class 12 or class 11. Okay. So I leave it up to you to check these things. So expectation of x square minus expectation x whole square is the variance. So this is 2 over lambda square minus 1 by lambda whole square. So this is what we get as an variance. Okay. So one of the important property of exponential distribution is that it is memoryless. Okay. So by memoryless, it means like, for instance, if let us say if I toss a lot of coins until I observe the first head, okay, and if we toss a coin several times, let us say, and if we don't observe a head, then from there onwards, it's like we start all over again. Okay, so it's like it's in the like binomial case we have seen, right? So so it's like I toss a coin, right? So let us say I keep getting tail, and then up to here I get a tail. Okay, so let us say this is some time t equals to n, or the trial nth trial. Okay, and so after this the outcomes I get. Okay, so the waiting time, also to say the waiting time that I have from here onwards to actually get ahead is dependent. Okay, in other words, like this up to here, it's like have no influence on what when I will get from here onwards, when I will get the head actually. So this is called memoryless property. Okay, so exponential is a memoryless memoryless. So we can explicitly write what we mean by memoryless. So x is an exponential random variable with lambda greater than 0, and then x is a memoryless variable if we have this. Okay, so this is the memoryless property if holds. Okay, so probability that given that x greater than a has happened, what is the probability that x greater than x plus a? Okay, so this remains probability that x greater than x. Okay, so it's like a probability that x a is here, and then from here onwards you have some x plus a somewhere here. Okay, so what this is trying to say is like whatever happened on the waiting time that you had until here, okay, has no influence on the waiting time you will have to have probability that x greater than a. Okay, so it's just dependent on x greater than x. Like it's like you are starting from here. So let us say this is like x equals to 0 case, and from here onwards you have this is length is x here. Okay, so what this is saying is like from here onwards, my waiting time, the distribution is not going to be affected by the fact that I had waited until x up to a. Okay, so this is how compactly we write a memoryless property. So we can prove this for the exponential. This is the proof here. So probability that x greater than x plus a, given that x greater than a. Okay, so this is by applying the definition of the conditional. So this is like intersection here. Probability that x greater than x plus a, and probability that x greater than a divided by probability that x greater than a. So this intersection is nothing but x greater than x plus a only. So and then everything is the same. So probability that x greater than x plus a is nothing but 1 minus CDF of x plus a. Okay, so CDF, remember, is fx x is like minus infinity to x. Okay, so CDF is like here, and what you are asking here is probability that so this is same thing as saying the probability that x is less than or equal to x. What we want is probability that x greater than x plus a. So this is same thing as 1 minus probability that x is less than equal to x plus a. So this is nothing but 1 minus fx of x plus a. Okay, so this is nothing but the CDF So this is what we have done here. And the same thing applies to the denominator. It's just that now we have a here. And we substitute the CDF. Okay. So remember the CDF of exponential was here, right? So CDF of exponential was 1 minus e to the minus lambda x. Okay. So this was the CDF. So we will use this. So we will use this, the 1 minus, so 1 will get cancelled here. So it will be exponential of minus lambda x plus a, and same here, minus lambda a. So, and then we will cancel out the exponential of lambda a, and that's the common term factor here. So, and then we will be left with this. And this we know is probability that x greater than x, right? Because we can, like CDF we know, right? So CDF, from CDF we know fxx was x was 1 minus e to the minus lambda x. So we want so exponential of minus lambda x is 1 minus fxx, but 1 minus fxx is probability that x is greater than x. So this is what we have written here. Okay. So what we have derived is the so-called memoryless property. Memoryless property. Okay. So this is what is called memoryless. So exponential satisfies this. Okay. Now what we will see is something called a normal distribution, or sometimes it's called Gaussian. Okay. So there is a like there is a saying that some engineers like to call it Gaussian, and mathematicians like to call it normal. Okay, so both are the same names. Okay, so how it is defined, once again, like all distributions are defined via their PDF, right? So here also we are expecting some PDF. So continuous random variable Z is said to be a standard normal distribution, or sometimes it's called standard Gaussian random. So you can already guess, like, if something is standard, then there will be something like non-standard, so to say. Okay, and no such thing like non-standard, but there will be like more general variant we will see. So the first step is to see what is the standard normal random variable. So the standard normal variable is denoted like this. So you can see these are the parameters. This is how we denote the parameter. Okay, I have missed writing something here, right? So this you can write like this, normal. Or sometimes people write shortly as n. Okay, n01. So this is the typo here. So this is the standard normal distributions, and you can like see that these are the parameters. And obviously, if I make these parameters more general, then it will be like some general normal distribution, but we will see that later. So if its PDF is given by this, okay. So this is the standard normal random variable. Okay. So these are the PDF, like one I mean, it's a very nice thing to memorize these things. These things have a lot of applications. That's why people have written down these things. So it's always good to memorize. Okay. So this is the PDF, and this is defined, the range is defined for all R. So this means like this is like a valid PDF for all of R. Okay. So unlike some of the PDF we have seen, like this somewhere, but this is like defined over all of R. And one thing we would verify is like the integration. So in this case, it does take minus infinity to infinity, fz, and this is something we have to check. Okay, so this is like check that this must be equal to 1, or in other words, what this will tell us is that what we have to verify eventually is that minus infinity to infinity e to the minus z square by 2 is this square root 2 pi. Now this is something you may have seen as an indefinite integral. So this is like indefinite integral. So you may have seen something like this. Maybe you have seen something like this in your 10 plus 2 or 10 plus 1, where you were asked to do problems like this, where you had to solve this. And so a good way to solve this, I can already give you a hint, or if not, then I will do this dz. Okay. So this will be like polar coordinate would be a better way to solve this. Okay. Yeah, so one can prove this this result, but I will like put it on hold, or you can do this in tutorial. But so this is what we have to verify. If we can verify this, and then if we normalize this, so now you can already see like this is acting like a normalizing factor. So we know that this is the square root of 2 pi. So if we have divided by square root of 2 pi, this becomes a valid PDF that we require for all the PDF. It should integrate to 1. So this is something we can keep aside for the moment. And if we plot this, then first of all, we note that is this an even or odd function, right? So it is even or odd. So you may have seen this thing. So during JEE preparation and so on, like knowing these things is very important in quickly getting to the answer, right? So even, odd, all these things. So this is quickly we can guess that this is like an even function, because f of minus z is f of z. So this immediately tells us that it will be symmetric about x equals to 0 axis. So that gives us the idea of that it will be symmetric. And then we also know that like exponential is like this. It's like a decaying. It's like a decaying function, right? As z is greater than 0, so it will start going to 0 and so on. And between 0 and 1, like something will happen here, right? So it will be like more like a, yeah. So e to the minus e to the x is like this, and then it's z square, so it will go a little bit. There will be a bump like this, and then it will eventually decay, even decay faster than minus x, right? So we get a fair idea of how to plot this, and this is continuous, obviously. So nowhere there is a jump or anything. So this is a continuous random variable. And what we also now know from here is that if we integrate this, so that is the area under this this curve. So this curve is the plot of fz z. Okay, so this is the curve. This is the curve which is the PDF, and what we have, if we integrate this, then it must come out to be 1. Okay, that's what all the PDFs should satisfy. So this is the area which is 1. Area is equal to 1. Okay, because this is a probability distribution. Okay, so these are the facts we know, that it's symmetric about the y-axis, and this symmetry is something that will be very important in some of the proofs that we will do, because some of the probability calculations and so on, we will see that we will use this symmetry a lot. Okay, so standard normal distribution or Gaussian distribution is the most important probability distribution in whole of probability and statistics. You can think of this is the most important probability distribution. So like we don't even hesitate to say this, right? So it's like I'm not even saying one of the most, right? So it's like I'm saying the most important probability distribution. So you can already see the importance of this. And one of the reasons why it's the most important probability distribution is so-called central limit theorem, and we will do this theorem. Central limit theorem. So central limit theorem, before going there, we have to do sequence of random variables. So I hope you have brushed up your sequence and series by now. So you will see that we will do this sequence. So now we have one random variable, functions of random variable we see so far. Then we will go to like multiple random variables. So then we talk about x. So we start with 2 random variables, and then how they relate and so on. And then we will go into sequence of random variables. Okay, and then we will talk about functions of multiple random variables. Okay, the function of x1, which is a random variable, x2, which is another random variable, and so on. So can be really generalized, and that's where calculus is needed a lot. So central limit theorem, what it says, like we cannot do this right now before I define all those concepts of multiple random variable. But in short, what this says is if we add a large number of random variables, like there are caveats like independent and identically distributed and so on. I have not defined those things, but for the moment, like let us not get into the technicalities. So if we add a large number of random variables, then distribution of the sum goes to like normal. Okay, so what this is saying is like if you add a add various random variables, let us say x1, x2, xn, so on, and let the here large means like I add like infinitely many of these independent and identically distributed. So I will get into technical things later on. So what happens is like these may be like different distributions, okay? But if I sum these, the distribution of the sum, okay, is converges towards the normal, okay? So like the mean and all these are like converging towards the normal, okay? Because for normal, what do you need? So remember, these parameters define these, right? So if I say, okay, if I'm saying that like the mean is converging towards 0 and the variance is converging towards 1, then okay, it's like, yeah, it's going towards the normal. Okay, so so these are the concrete proofs that we will do, but before that we need some technical. So so why it's important? It's important. One reason that you will see is like central limit theorem, and in general you will see that many of the distributions you will see, they follow some kind of a bell curve. Okay, so they follow this kind of, even the like the marks that you obtain, most of you actually will follow the bell curve. So sometimes during grading also, like we can get some idea of the standard deviations and so on, variance and so on. Okay, so many realistic data actually follows so-called bell curve if the number of like if it's really like a large okay. So we will get into this, like how like central limit theorem really relates things to normal. And then yeah, once, yeah, and that's why normal is like really well studied. Like there are many things, tabular data and so on. So okay, so I think it's not appropriate to say too much right now. So here, as I have already motivated you, that 1 over square root 2 pi is the normalizing thing, because we know that integration of minus z square by 2 minus infinity to infinity is indeed square root 2 pi. So this is something, a calculus result we can prove, and then 1 over 2 pi it will act like a normalizing factor, so that area under the curve becomes 1. Okay, so what we have is the first result. Like whenever we write a distribution, we always claim something about expectations and variance. Okay, so these are the most important properties of random variables. Of course, other important properties, if you're working on like higher dimensional data and you want to know like higher order correlations and so on, then you go for higher order moments. Okay, so this is like the second order moment is like the variance, and then if you want to extract more from there, you may go for higher order moments like third order moment, fourth order moment, and so on. But as a start, you can see what is the average value that the random variable is taking, and what is the spread of my random variable. So these things are denoted by expectation and variance respectively. So let us try to establish this fact, and this should be like rather straightforward. Once again, like I have done already this many times. Like if g is an odd function, then and integral is defined to be like valid integral, in the sense like the integration number that we get is like less than infinity, then we know that it's symmetric about the y-axis, and the integration should cancel out, the negative and positive area cancels out, and we get 0. So I've just written it up, but we already have discussed this already like many times. So so this is like the result of the odd function. Integrate odd function about the symmetric limits. So this is like symmetric limits, then the integration cancels out. So this is something we are going to use it in the expectation, because expectation will require z and fz. So fz is even, but if I multiply by z, it will make it odd. Okay, so that is how we are going to do. So let us do this. Let us do these calculations here. Okay, although this is trivial, so I will quickly go through this. Okay, without wasting too much time. So expectation of z, right? So expectation of z is the normal, right? So z is the normal, and it's like 0, 1. Okay, it turns out that this parameter 0 and 1 you see are nothing but expectation. So let us calculate this. So this is like minus infinity to infinity, and this is like x 1 over square root of 2 pi and e to the minus x square by 2 dx. Okay, so this is like a odd function. Okay, odd function. Overall, this is an odd function. So and symmetric about y-axis. So this must be 0. Okay, so this is an odd function. So this is done, and then for variance we need expectation. So expectation of z square is like minus infinity to infinity, and then we need x square here, 1 by square root of 2 pi e to the minus x square by 2 dx. So what do you think about this? This is an odd or even function? So odd or even? What do you guess in the chat? Even. Okay, Akash, even. Good. So this is an even function. So for even function, we know that the integral, the area is like like equal on the both sides. So that's what we know for the even function. So we will invoke that, and so we can invoke that, or like even like we can like directly do this integration. It doesn't matter. Okay, so even if like so we do integration by parts. If we do integration by parts, and if we do integration by, and what we will get is 1 over 2 pi square root 2 pi. So so yeah. So if I do integration by parts, then what do I get? So if I do integration by parts, like so this like yeah, so we can choose. So which one should I take the first function? Is easier, right? So which one is preferable to take as a first? Like one thing what we can do is like, okay, does it make sense to substitute x square by like something like u or something, right? So that might make things easier, right? So let us substitute x square is u. Okay. So does this make things easier or not? So we have like 2x dx is du, but then x will be there, right? So it doesn't seem to help that much, I think, because then x will be there and then the square root of u will come out and so on. Okay, so yeah, so we have to like recall our integration skills. So did anyone do this integration already? What do you expect? So 1 by square root of 2 pi we can take out. Okay, and this is like minus infinity to infinity x square e to the minus x square by 2 dx x square. Okay, so what do you suggest? What is the way to like integrate this? Like this is even, that is clear. Okay, this is even. So it is possible that, okay, I can like simplify this. So let us say it's like 0 to infinity, and then I multiply by 2. Okay, so that's because of the even functions I can do this. Okay, so now we are supposed to integrate this. So what does your integration skill tells you? What should be the answer in this? In this case, after I integrate this. Can you do this integration? So if we focus here, right? So this is the integral x square e to the minus x square by 2 dx 0 to infinity. So let us say this is the first function and this is like the second function, right? So the first function into integration of second. So this is like first function into integration of second minus of integral of differentiation of the first. So differentiation of first into integration of the second, right? So e to the minus x square by 2 dx. There's 0 to infinity, 0 to infinity. Okay. So this is the integral that we are supposed to calculate, and so this will come out to be how much? So this we have seen before, right? So this is the 1 by how much? Square root of 2 pi. Square root of 2 pi. Square root of 2 pi. And this is like half of that, because integration of minus infinity to infinity e to the minus x square by 2 dx was this, right? And this is like 0 to infinity, and then this is like an even function, so it would be like 1 by square root 1 by 2, and then square root of 2 pi, and so on. Okay, and this is like x square will go from like 0 to infinity. Okay, so x square will go from 0 to infinity, so I think it's like this. Okay, and if we compute this also, so this will be how much? So what is the result of integration overall? So what we will be left with is 1 by 2 times 1 by square root of 2 pi, and then e to the minus x square by 2. I think this term will go away, isn't it? Okay. So I think what will be left with is yeah. So what we will be left with is something like this: 1 by square root of 2 pi, and it's 2 times of that. So overall, and 0 to infinity, and then e to the minus x square by 2 dx. Okay, so but we know that this is like 2 times the, okay, yeah. So what will be left here is 2 times 0 to infinity 1 by square root of 2 pi. Okay, and then exponential of e to the minus x square by 2 dx. Okay, and then this guy will be square root of 2 pi. So what will this come out to be? So this is like 2 by square root of 2 pi 0 to infinity e to the minus x square by 2 dx, and this will be 2 by square root of 2 pi, and this is like this is like half of minus infinity to infinity e to the minus x square by 2 dx. So this we know is square root of 2 pi. Okay, so this gets cancelled, this gets cancelled, and this comes out to be 1. Okay. So you can work out this differentiation. Okay, I have outlined this, and eventually the term that is left is this, and if I go on and calculate all these things, and it comes out to be 1. So I believe you can verify this these results. Okay. Okay, so the CDF of the standard normal distribution is denoted by phi, which is nothing but this, and this will be found by integrating from minus infinity to x. So that's how the CDF is defined, right? So CDF is defined by integrating from minus infinity to x. In this case, the valid lower integral is indeed minus infinity. So this integral does not have a closed form solution. Okay, so this integral doesn't have a closed form solution. We cannot really find a closed form solution for this. So there will be like tabular results for this. Okay, so we will rely on some tabular data that I will let you know later. So fz, the values of fz will be like tabulated. Okay, fz, or you can talk of like it's the same thing as f z. Okay, so this is the same thing as okay, let me do x. Okay, let me do x here. So so this is like another notation for us is like if I'm using z, as a normal distribution, then let me stick to z. Otherwise it will be, so this is like z and then x. Okay, so this is the CDF, but we are using some other notation as well here. Okay, which is like phi of x. Okay, so we use this interchangeably. This is a very standard thing to use phi function, so-called phi function in when using normal distribution. So should not get confused with this. So this phi x is nothing but the CDF. So what we say is like this data has been tabulated. Okay, because this integral is not, we cannot find a closed form solution for this. Okay, when we are computing expectation and all, it was a bit easier because it became order even and so on, and then the limits were minus infinity to plus infinity and so on. But if you see just on this type of integral, if you focus on this, then you don't have any closed form solution for this. So you have to rely on some tabulated data. Okay, for this. So if I put x equals to some, let us say something, let us say half or something, then we have to look up into some table to get the answer. Okay, these tables will be provided in the exams. Okay, the CDF of any normal distribution can be written in terms of the phi function. Okay, okay, so wait a second. What am I? Yeah, wait a second. So like what I see is this is isn't this the CDF already? Like what am I missing here? One second. Yeah, I need to like verify this, right? So CDF is already, like we know CDF is fz of x is like the probability that z is less than equal to x. Okay, so this is the CDF, and which is what I have defined is to be a phi here. Okay, so for me this is exactly the CDF. Like why am I saying can be written in terms of phi? I don't see why can be written in terms of phi. For me, it's like CDF right now, or unless I'm missing something here, I don't think so. Okay, let's go ahead and see if there is anything here. Okay, so phi x is nothing but the area. Okay, which is nothing but the CDF. Okay, so this is the area under the curve up to the point x. Okay, so this is what I have plotted here. So phi x is like the area function. Okay, so the phi x can be plotted separately here. Okay, the phi x is not this curve. Phi x is just the area function. Okay, so if I plot the area, then the function or this curve denotes the area value. Then this will go like this. So it will go like at 0 it is half. Okay, because it's symmetric about the y-axis. So and we know that the complete area like should be like 1. Okay, so we know that up to half the area value should be half. Okay, that's why we have at 0 it is half, and then it should converts to 1. Okay, so that's what, as x tends to infinity, we know that the area under the curve is indeed 1. So that's why it becomes flat after this. Okay, so it's just converging to, it's not like it is approaching to 1 asymptotically, right? So it's only 1 at infinity, right? Because it is decaying, it's not, it does not reach exactly like 1 at some point, right? It slowly goes to 1, so it's approaching to 1. Okay, so this is the phi x function, and which is nothing but the area under the PDF of the normal. Okay, distribution. So we can identify these properties straight away. So for instance, if, and this is like phi x here, which is missing. Okay, so this is phi x and this is like phi x. So as x tends to plus infinity, phi x is tending to 1. So this property is verified here. And x tends to minus infinity. Okay, so the area will decrease, right? If you go to x tends to minus infinity. So area is approaching to 0. So that's also correct. Phi at 0 is half, like I explained just now. So at 0, it should achieve only half of the area value. Okay, the total area value should be 1, and at 0, because it's symmetrical, at up to this point you have covered half of the area. So naturally at x equals to 0, the area that you compute must be half. And phi of minus x must be equal to 1 minus phi of x. Okay, so how do you prove this result, right? So phi of minus x is 1 minus phi of x. Okay, so what do you, so x is here, right? So minus x will be symmetrically at the same distance, but somewhere here, right? So somewhere here is the phi of x minus x, right? So this is like minus x. So why do you think this result holds? Like phi of x, phi of minus x is 1 minus phi of x. So why should be the case, right? Look, phi of x is like area under this, right? So phi of x is the area under this, and phi of minus x is the area up to here. So what this is saying is like area up to here plus the area up to here must sum up to 1, right? So do you see like symmetrically, what does this mean? Or in other words, my question is, what is this area? What is this area? So can you tell me in the chat, what is this area? What is this area that I'm talking about this area, right? So what is this area? Phi of what? Phi of minus x, Varul. Okay, great. So this area is indeed, this area, stated area, is nothing but phi of minus x due to symmetry. Okay, so some of you are saying symmetry, that you are also correct. Okay, but to prove this, what we need is like phi of x is this area we have computed. Okay, so far this area is computed, and remaining area we know is phi of minus x. So phi of x plus phi of, due to symmetry, phi of minus x, this area must match this remaining area. Okay, so this is like, so phi of x plus phi of minus x must sum to 1. So that's what this result is saying, right? So phi of x plus phi of minus x must sum to 1. So this is the proof that we did. So like it comes from symmetry observation and so on. Okay, so all this property hold. So in other words, this also tells you like from the tabular result, sometimes like you see sometimes that from the tabular result, sometimes like x may be given to you, and then you should not say that I don't know minus x in the table data. Okay, because you can be computed from this identity. So the tabular value may be given to you only for the positive values of x, and for the negative values, you have to get those data by doing this 1 minus phi of x, maybe using calculator in exam or so on. Okay, so this will be like expected from you that you know this. Okay, so so these are the identities that you should literally mug up. I will keep telling you that probability is becoming a very important area subject. It applies in regardless of like domain you can think of. So be careful not to take this subject lightly. You want to go for higher studies. Probability is the must. Okay, even in like coding placements, they ask a lot of probability questions. Okay, so okay, so the bound for phi function, right? The bound for phi function is the following. Okay, so this is the standard normal, because it's the parameters are 0 or 1, then it's called standard normal. And then phi x is defined to be like this, probability that it's like less than equal to x. Then for all x greater than equal to 0, okay, like due to symmetry, it's enough to prove results for x greater than equal to 0, as I said, okay, because for minus x, I can just derive those probability results by doing 1 minus of that, okay. So the phi function satisfies the following. Okay, so the phi function satisfies that. So this is like more like some maths result, like some bound and so on. Given what phi function is, like how can you establish such bound? And these bounds will be useful like some when we are proving some result or so on. So attempt to prove this this result. Okay, so this bound is like an important result. So we can like prove this. So what are the things we are given? Given that this is a normal, and we are given that x is greater than equal to 0, and so 1 minus phi of x we can immediately see, right? So 1 minus phi of x will be the negation of this. So 1 minus phi of x will be 1 minus probability that z is less than equal to x. But we know that complement of this is probability that z is greater than x. Okay. So in other words, what we are saying is like probability that z is greater than x satisfies this as a lower bound and this as an upper bound. To show the upper bound, so let us prove case by case. Usually bounds we prove case by case basis. So yeah, we can try to do. So to show the upper bound, So to show upper bound, what we have is like, first of all, we notice like what we are seeing this guy as nothing but probability that z is greater than x. So what we have to prove that probability that z is greater than x is less than or equal to this term here. Okay. So what we have is probability that z is greater than x is equal to. So first of all, we write the definition of that probability that z is greater than or equal to x. Integration from x to positive infinity. That's how these properties are defined, right? So this is like x to infinity and e to the minus u square by 2. Let us use the term u because x is already used in the limit so that we don't confuse later, right? The integral we have, and now we are going to use some trick. Okay, so this trick may not be very trivial to use in general, but let us see this. Okay, so this is like less than equal to, and then I think we also need this 1 by square root 2 pi, right? Because this is like in the PDF, right? So this is like 1 by square root of 2 pi, and the trick that I'm going to use is x infinity, and then what I will do is like u over x. Okay, this will look very funny for the moment, but let us do this. E to the minus u square by 2 du. Okay, so and what I am claiming is also less than equal to. Okay, and since I'm integrating over u, obviously u is greater than equal to x. Okay, so obviously u is greater than equal to x because that's the limit of integration for u. So u is greater than equal to x and x is greater than equal to 0. Okay, so what does this mean? Like this means like the u divided by x, right? So it's like greater than equal to 1. Okay, so here so this inequality will hold. Okay, so this inequality will hold. I mean, there is no ambiguity in also saying x is greater than 0. Okay, because singleton points doesn't make any what to say, like any change in the probability in the continuous case. Okay, so it's safe to say that x is greater than 0. So u by x is like greater than 1. So this is like a dominating term, right? So this is again coming from the from the integral, right? So if fx is less than equal to, so this is like recall calculus, right? Dominating, what was this called? Dominating function theorem or something? I don't remember those names, but I remember these results. Okay, so it's like recall. I think the something like that it's called. Right? So fx is less than equal to gx. Let us say in the interval x a b, then integral of fx dx is less than equal to ab, is less than equal to integral gx and dx. Like, I mean, this is like trivial, right? This is like obviously like the area fx gx is greater than equal to fx, so it's like this. So obviously the area under G is going to be bigger. Okay, so this is like obvious, you can say. Okay, so this is what we have done. Like this function overall, this is serving us like a Gx, and this is like fx, or in this case you can talk like fu and gu, right? So dominating function theorem or something like that in the integral that tells us that the integral will be greater than equal to 0. Okay, that's why we have a greater than equal to in this here. Okay, so this makes sense. Okay, now x is not really like a variable here. Okay, because the variable here of the integration is u. So x is like a constant, so it can come out. Okay, so this is the equality here. So 1 over x. Okay, and then this is like we have to like integrate this u times this. So this is integrable now because it's u times e to the minus u square by 2 du. And if we do these calculations, then 1 by square root of 2 pi 1 over x, and if you do this, then it will come out to be minus u square by 2 x to infinity. And if we compute this, then 1 by square root of 2 pi 1 over x and e to the minus x square by 2, because the infinity term will go away. Okay, so this is the, okay, we are almost on in time. Yeah, I think I may have to stop now. So this is the lower bound. We will try to prove the upper bound. Okay. Yeah, so I think that will be all for today. Okay, we will continue this in the next. So revise your integration and so on, sequence and series. Okay, we will be using that. Also, multivariable calculus will be needed when we will do joint probability. Then you need to know the partial derivatives. Okay. Anyway, like I will revise those. Like I'm revising those anyway, but basic things, if you can recall, it will help you. Okay. So let us stop here, and yeah, see you in the next class. Have a nice day and bye.